Right, it's good. All right, we can start now. So yeah, we'll continue with the beyond Trotter fault tolerant procedures, and LCU and qubitization will be the method that we will discuss today. Now, the idea is that we would like to encode the Hamiltonian somehow into quantum algorithm. The motivation is very simple. We now know that if we want to extract, say, eigenvalue of an operator, and if we can put it as a phase factor, then there is a way to use quantum Fourier transformation to get that phase out, right? So, and that's the whole idea. But there are multiple ways of putting the necessary quantities as a phase, okay? And today we will look at the method that may look complicated, but it has origins that quite simple actually, and hopefully you'll get the basic idea how this can be done. Alternative, of course, to the Trotter or just exponential way where you just exponentiate the operator. Then if such operator meets the eigenstate, then the eigenvalue will get inside the phase, right? So that we all know from the sort of quantum mechanics 101. Right, so then we can extract it. Yes. Is it good? Okay, great. Cool. So the basic idea with this linear combination of unitaries, we're gonna try to, or we will put H, which is not unitary, as a part of bigger unitary, and that unitary we will call actually Walker operator. Somewhere here in some corner of that bigger unitary, there will be our Hamiltonian normalized so that it won't break the unitarity with its H norm, right? And then we'll be able to extract the information, right? So that's the basic idea. And one of the tools that we'll be using is this nice opportunity that more qubits will allow us to have. And what I mean by that is if you have unitaries, let's say, in the same space, like if you have n qubits, and then you have n qubit unitary 1, if you add it to n qubit unitary 2, then it's not unitary anymore. So there is no closure with respect to addition. There is a closure with respect to multiplication, but that doesn't help. So turns out if you go to the larger space, let's say we extend by a single qubit and go to the n+1 qubit space, then we could organize a projector, let's say projector to the 0 state of this extra qubit that we added, multiplied tensorially with the U1, and the projector on the state 1, this extra qubit multiplied by U2. And that allows you to still have unitary, even though it's a unitary in the larger space. Okay, so technically what was happening is that in the space that we start working, those two unitaries sort of overlap and broke unitarity of each other. And then when we added one qubit, extra qubit, we're able to kind of separate them into subspaces, which are not overlapping, right? So this projector and this projector, they are not overlapping, meaning that if we call this P0, this P1, so any product of P0 with P1 will be 0, right? So there's no overlap. The structure of this unitary, the bigger one, will be that U1 stays its own subspace where the extra qubit in this state, NU1, NU2 stays in this, right? So then you can add unitaries easily if you prepare for each of them a separate subspaces that technically still form the entire space, because P0 plus P1 is identity, right? And that's exactly what is written here, that we could build bigger unitaries. We will use this motif in our considerations by attaching to separate unitaries the projectors.
Sorry.
Yeah.
So just my understanding. We are now not talking anymore about implementing the time propagation, but the Hamiltonian itself as a sum of unitaries. Or because I mean, the time propagation is a unitary to start with. So.
Right. So the time propagation is a constraint that is not really needed if you like. Who said that the time propagation? Well, what was the time before? There was no time.
Exponentiation of the Hamiltonian.
Right. Exponentiation of the Hamiltonian is one way to take the Hermitian operator and put it in the sort of a form of a unitary operator, right? So the time was not really important there. It's rather we just unitarized the Hamiltonian. Hamiltonian carried all the information about the system, and that's what we wanted to put the information about the system in a unitary operator form. And then there was a kind of quantum Fourier transformation to extract the phases that we will be getting, right? So time wasn't that important, and actually in this QPE, time is sort of discretized and really is just the steps of the process. So that it's not a real physical time, right, anymore. So now in this new context, what we are thinking about is how to put the Hamiltonian as a unitary operator. And for that, we will be using not exponentiation, but some other construct. So like the starting point is that we will present H as a linear combination of unitaries, and then we will add them up to the larger unitary. But it's not so simple, because once you start adding unitaries, you can easily break out the property of unitarity. Therefore, not to break that, so the next step is, well, you could introduce the projectors. For introducing the projectors, you need bigger space. Okay, so that's kind of the idea.
So that's essentially the price that you pay, right?
Right.
You have a much larger space.
Yes, and that one big difference between Trotter based methods and this linear combination of unitary based methods, because in this LCU based unitaries, for accommodating these projectors, you need to introduce extra qubits, and those are not the same extra qubits we need to measure our phases. So we have two sets of extra ancilla or auxiliary qubits, not to confuse them. Right?
That's why the Trotter way might still be nice for early fault tolerant.
That's right. Yes, that's the main argument, that the Trotter, even though it has an error and it scales quadratically with time, not optimally, this method will scale linearly with time. But the issue is that you have more. You need to introduce more qubits. Okay, those qubits, depends. If we are thinking about fault tolerant qubits, those are logical qubits, and they require error correction implemented there. So indeed, the resources will grow, even though the number of operations may be better with the LCU rather than Trotter, because for the Trotter, you will need to discretize and make the time steps or your steps of the algorithm smaller, and that to control the error. And here you could do larger steps, and therefore kind of number of operations could be smaller, right? Okay, but going back to the algebra, essentially the final point, just to give you an idea, the final point with all these algebraic manipulations is that we're building, instead of exponential function of the Hamiltonian, this interesting construct that is called Walker operator. So you could think of a Walker operator as something analogous to, let's say before, we had a sort of we discretized time, and we had this as an elementary step of the process. Then we did the trotter, but essentially we represented this using a, let's say, first order trotter as a product of our fragments delta t, right? So that was the version of our Walker operator. So we made the walk with steps like this, and in this new formalism, the steps are made using this operator, which looks interesting because, well, it has normalized h, that's why I put tildes. But one thing to recognize here is that this is just a part of the operator that we'll be using. So the operator is a little bit bigger, but there is a part of the operator that looks like this. And you could convince yourself that if you have the operator like this, then it's an exponential function of I times arc cosine of that operator multiplied by Pauli Y matrix. Why Pauli Y matrix? Because, well, we're working with two-dimensional subspace. Anything can be, any operator on two-dimensional subspace could be written as a linear combination of Pauli matrices. And so, so that this will look, this transition will look natural, or we could just do the simple algebra. So what do we have here? We exponentiate the operator that is kind of involutory, right? Because we know that technically sigma y squared is identity, right? And if you do this exponentiation using formula from the earlier formula, really, we will get the result that is for anything like this, the result will be cosine of the amplitude, right? Cosine minus 1h. Then we will have identity plus I sine of cosine minus 1h sigma y, right? So that's the usual formula. And then you could simply convince yourself that from elementary, here we are dealing with the operator, but it's like all functions are analytic. So you could substitute this by the usual relations like it's just h, because it's cosine of arc cosine. Sine of arc cosine is just square root of 1 minus h with tildes for the normalization. So we don't want to have a square root of 1 minus something that has a norm larger than 1. Okay. And then what is left is here, right? So what is left is sigma y multiplied by I. That is well, sigma y is minus I, right? And then if you multiply it by I, you're gonna get 0, 1, minus 1, 0. Okay, and so then the answer will be essentially h tilde, then the multiplication with identity of 2 by 2 subspace plus square root of 1 minus h tilde squared. Then the product with this matrix of 1 minus 1, 0, 0. And that's what we see there as a Walker operator. This is how we can construct this. Now, why this form is nice? Because, well, first of all, it's kind of clearly shows that things are now unitary, because this is product of Hermitian operator with something also Hermitian. They commute, and so then times I, it's anti-Hermitian. So exponential function of anti-Hermitian is unitary, clearly. And also the quantity that like here, h was meeting the eigenfunction, getting to eigenvalue. So in this case, if we bring the eigenfunction of H, then we'll get eigenvalue in the arc cosine, right, as a phase. And then what do we do with the phase? We extract it using Fourier transformation, right? So that's a nice idea. And note that the function that we get here is non-polynomial, so which is surprising because after all, it's not that easy to put non-polynomial functions out of fragments, without any error. Okay. There is only one caveat that to normalize H, we see that it needs to be normalized by the one norm of coefficients in the LCU decomposition of H. So then the whole game of optimizing this, like we played the game with Trotter, how to optimize the fragments. Here the game will be how to reduce the norm of coefficients. You could, of course, use multiple fragmentations to unitaries. If someone gives you Hermitian operator, there are multiple ways to do this, and some ways are better than others. And that's a little bit complicated matter. It's more complicated than just looking at the cost, like looking at what expansion has the lowest one norm, because then we need to implement those unitaries on a real quantum computer, and some of them are harder to implement than others, right? So then there are these considerations also get into the picture. But in the first, it's like, I guess in the first approximation, one norm could be considered as a variances, right? Which we considered in the measurement problem. Variances were defining the number of times we need to measure, but of course they didn't really we didn't concern ourselves with the part where which unitaries do we need to put, like whether they may introduce more errors because there are more operations involved, right? So then one norm is a good first approximation to how difficult or how expensive this LCU decomposition will be to implement. Okay. All right. Now with this, let's see. This is the circuit. As you can see, it's 2018 paper by Google folks. And this is the circuit for the qubitization algorithm. Now, this circuit should remind you essentially the quantum phase estimation circuit. The difference is essentially there's again the same three parts. Initial Fourier transformation that they do in a more sophisticated way to get the high accuracy, and but that's not really essential. Essentially, they are preparing the state which is somewhat different than the state prepared here, and then quantum phase estimation, not phase estimation, but quantum Fourier transformation reversed. The measurement exactly the same steps, and the only difference is in the middle, because now we are not trying to introduce controlled exponential functions of the Hamiltonian. We introduce this Walker operator with some extra steps. But essentially, you could think of it as if someone implements this operator, then doing the quantum phase estimation on it will provide you the phases that are necessary for the extraction arc cosines of the eigenvalues, and from that you could classically compute what the eigenvalues are. Okay.
Didn't you say we need a second register of Anchilas? I don't see that in the circuit.
Right, they will be in implementation of the Walker operator. Yes, so this is indeed the first set of ancillas, but in the Walker operator we will need another.
And then we need a controlled Walker operator.
Yes. Yeah.
Is that more? How does it compare to controlled unitaries in terms of, like, I don't know?
Well, Walker operator is a unitary, but it's a complicated unitary. It lives in a target plus the first set of auxiliary, right? So, but generally, any controlled operator is just, as we know, control U is simply zero projector on nothing, plus the one projector on whatever unitary you want. Instead of just having a unitary, you need to have this. So yeah, there are standard ways which you could read about, and I don't wanna. And actually, right now I won't be able to tell you what's the most efficient way of doing this currently, but it's it's kind of could get complicated, right? Of course, but there are ways to do it, as always. So if you essentially there are standard ways if you have a unitary to build the infrastructure to introduce the control unitary.
And sorry, one more.
Yeah.
So we use this walk operator as an alternative to implement fate and can extract. So it's not necessarily, or in normal QPE, time propagation was just a means to getting that. So I was just wondering, can you use this walk operator and also the Krylov methods where we want to have time propagation in the sense of what it is? The Krylov methods want to do time propagation.
Okay.
Versus this one is just a means to implement the phase, but
right.
that also works for Krylov.
Right. So when you say time propagation, you're interested in kind of simulating dynamics.
Yes, I mean.
So there are ways to do it with some modifications, but as you could see, the Walker operator itself is not linear function of h in the exponential, and somehow you would need to, make essentially steps between the walkers so that these changes in the phase need to be corrected so that it actually approximates dynamics rather than simulates this.
But maybe it's not important for Krylov method. I mean, does it really matter if it's not linear?
When you say Krylov methods, you're talking about the finding eigenvalue, right?
Yes.
Okay. Right. Yeah. So then finding eigenvalue, yes, you could use that, but that comes with the price of extra qubits, I guess. Yeah. So, but generally, yes, you could use that.
You have the problem in Krylov methods of Trotter versus time step. So if you don't have a Trotter error, you might get rid of that problem in these Krylov methods.
Right. You could do it this way, yes.
I don't know. Maybe that is a problem.
Well, people, I guess, mostly concerned that it will, take a lot of qubits, and they, don't mind Trotter error that much, but cannot say what would be the right way to think about it. After all, there are cons and pros, right? But yes, you could generally use this technique to generate quantum Krylov subspace. Okay, so with that, just we could focus on the how to construct omega or W, right? And the basic idea of construction is really related to a very simple fact from the, again, operator theory. I wouldn't even call this as fancy as operator theory, but the idea is the following. If we have two reflections, those are the unitaries that are Hermitian also. Pauli products are reflections. The eigenvalues are just plus minus one, right? And because they're Hermitian, so they need to be real, and they cannot be complex as just for a general unitary, right? And then therefore, you could think of the reflections as easy unitaries, but the problem is that they cannot carry this like a rich spectrum, like say spectrum of the Hamiltonian, right? They sort of interestingly have the information compressed. But then if you have two reflections and they don't commute, right? So if you multiply R1 by R2, and then because they're unitary and Hermitian, sort of, so then you could always have this, right? So the squares is 1. But if they don't commute, R1 doesn't commute with R2, you could check easily, don't commute. that this is not reflection anymore. If they do commute, then the product of reflection is reflection. It's like, if you remember from linear algebra, product of two Hermitian operators is only Hermitian if they commute, right? If they don't commute, then it's not necessarily Hermitian, right? But here, if they don't commute, then you get unitary operator. So this could be very simple spectrum-wise. This could be very simple spectrum-wise, but the unitary could be, well, more complicated and have a richer spectrum. And then there are these algorithms that are in quantum computing not related maybe to directly to quantum chemistry, like Grover you may have heard, and amplitude estimation. Grover is really amplitude amplification, right? So all these simpler algorithms, they use this construction where we build the unitary that does the work we need as a product of two very simple reflections. And why I'm saying the reflections are simple, because, well, any reflection can be thought as a 2 times projector minus 1. And the projector is sort of probably one of the simplest operations there, right? So reflections are the next in line. Now, they have also clear geometric meaning that, well, reflections is very visual. And therefore, just very simple illustration, hopefully, that how you could think of a Grover algorithm or amplitude amplification. So if we have, usually in those algorithms, if we have some initial state and we have state of interest, we sometimes call it marked state, and then there is the rest that is corresponding, well, we're thinking as an orthogonal complement, right? And then because of normalization condition, beta is here is 1 minus alpha squared. Okay, so imagine the situation where alpha is small, alpha is close to 0, and what the, I guess, Grover algorithm is doing, it's trying to rotate, find the steps, unitary steps that will rotate this function psi to function psi prime, or here if we use n times, like psi n, where alpha n will be much larger than alpha and close to essentially 1. Okay, so that's the idea of amplitude amplification or Grover algorithm, because they both trying to improve that. Turns out that the unitary that does this also has a form where this unitary has eigenvalues I theta, and these thetas are related to actually thetas are related to the alphas as being that there is a it's alpha, which is a sine of theta divided by 2, right? So initial alpha. So what this is essentially saying in all these Grover algorithms, I will show you very simply how to construct a unitary that, first of all, can kind of increase the amplitude of the state of interest. Let's say you have a state and you have some state of interest. And by state of interest, of course, it's a little bit vague. So you need to know something about the state you want, or you're interested in the state that you have, right? And then there is a unitary to construct, and essentially it serves two purposes. On one hand, you can enhance the amplitude of this, and then if you measure, let's say, this state, then with high probability you're going to get it, right? that's how Grover works. Essentially, there is a state that we're searching for. It's like some binary representation of some information, right? We don't know it, but there is a kind of a procedure that could recognize well, that this is the right state. And then if you want to find it, eventually you want to measure. But if you measure initial function, the probability of measuring this state is alpha squared, which is very low, right? So you want to improve alpha first, and then measure. That's what Grover does. But on top of that, if you know this unitary, see what you can get. Essentially, using quantum phase estimation, you can get the amplitude here, which will give you phase will give you amplitude of that state. Okay, so you could measure the amplitude very accurately because it's related to the phase. Okay, and so how is this done? In all these algorithms, it's you're doing essentially unitary as two reflections. One is a reflection around the phi state, and another is around the psi state with a minus sign. Okay, what this means is this r phi is 1 minus 2 by phi, and this minus r psi is 2 psi minus 1. Right? So these are the two reflections, and they what they do, they essentially geometrically, usually people show it on the circle. Why we can draw this circle is that it's easy to show through the algebra just by applying this to the state, right? So let's say what we do is we apply this, we apply this to the state, which is psi, and the psi is this, right? So we can show that all you get is back some modified phi plus some well, 1 minus, and I guess I can use the notation. The first iteration, the first application of U is generating alpha 1 and alpha 1 squared with the phi orthogonal. Okay, and that's then the two dimensional subspace where we do the rotation essentially, because unitary is generally a rotation in the space, and the reflections are geometrically, you will see, let's say if we start with something that have a relatively small phi component, this is the phi vector, this is orthogonal phi, right? So then the sine of this angle, let's say the angle initially theta divided by 2, the sine of this angle is this alpha that we have, and the cosine is beta, right, or 1 minus alpha. And then what's happening with this process, you could just simply do the algebra, but geometrically, what happens is if you do reflection like this, it alters the, it switches essentially the component of phi to minus. So whatever it was, it was alpha, right? So then after that reflection, it will be minus alpha. So that corresponds to essentially going from here to here and getting the state. This is the initial state. This is the state after first reflection. And then, so it should be symmetric. And then the next step is minus r psi. And that step is what it does, because it's minus, it doesn't really change the component of psi, it changes the opposite component, because whatever, okay, so the first step, let me say, if we apply r phi to psi, what we get is minus alpha phi, and then we get the, well, simply speaking, minus alpha squared phi dagger. And then we apply the second step. Second step to this function, which I will call, yeah, did I call it already? Yeah, psi1. This is psi1. If we apply r psi with minus to psi1, psi1 can always be written, of course, as a essentially psi1 as a psi initial function with some coefficient, let's say gamma, plus psi orthogonal with delta, right? And then what this next reflection will do, it will change the plus here, the coefficient in front of orthogonal, to the minus. So because that's how it works, you could just write things down and see it. And so what this corresponds to is a reflection around the psi, but the change is going in orthogonal space to psi, right? So then in one step of unitary that is done like this, you go from here to here. So as you can see, you're improving because you want to come close to the essentially the as close to phi as possible, because if you coincide with phi, that means your alpha becomes 1 and this part is 0, right? Of course, you can overshoot. There are ways to estimate how many steps you should be doing, but this is the idea. And then there is if you do more algebra, then it's easy to see that really the unitary that we have here is something like cosine of theta, sine of theta, and minus sine of theta, cosine of theta. So that's the unitary in terms of in terms of the theta. If you assume initially that parametrization alpha is a sine of theta divided by 2. From this geometric picture, you could see that what happens after the first iteration, you're gonna get the angle, which is 3 theta divided by 2. So it's like you rotated by one single theta. Okay. And so then we all know that the unitary in this two-dimensional subspace will have eigenvalues plus minus 1. Plus minus I.
So this unitary implements the projection based, the product of projections.
Product of reflections.
Reflections, sorry.
Yeah, because product of two projections is a projection. But this is a very general construction. Two reflections give you unitary, and that unitary carries some interesting information, and that happens in many places. And turns out the same idea happens in the building the Walker, but the Walker operator is more complicated. That's why I want to show first the simple ones that are easy to grasp, because here everything is happening in the two-dimensional subspace, and yeah, it's a very easy way to think about things. Now you could, whenever you work in two-dimensional subspace, you could do the algebra using Pauli matrices, interestingly, and yeah, so you could write down essentially this R and this R psi as Pauli matrices, because and that's a more like algebraic way of seeing the same thing, because this is more geometrical way when you look at various reflections, right? But there is an algebraic way where you could say, all right, like in the case of when do we have Pauli's? When we have 0 and 1 state, right? So this will be associated with 0. This is with 1, right? Then this will be simply sorry, let's put 1 here and 0 here. Doesn't matter, but This is the notation I use in my notes. So this, you can convince yourself, is simply sigma z then, because it's if this is identity, then you just subtract the projector to the one state. This becomes like a 0, 0 minus 1, 1 state. And this you could write as a little bit more complicated expression, but still relatively simple. It's actually, let's see, it's cosine of theta sigma z plus or minus cosine sigma z plus sine theta sigma x. And then you could easily do the algebra. If you make a product, sigma z will cancel sigma z, we'll get identity, but sigma z times sigma x will get sigma y. And well, then it's easy to, it's easy to see that in this kind of, you could think of it as a Clifford algebra, because we introduce the generators of which are Clifford algebra generators. And then what we get is the expression that looks like sine of theta times I sigma y minus cosine theta identity, right? And that is simply a minus, right? Yeah, so it's a minus exponential function of I theta sigma y. Yes. Right, so this is the operator. Then clearly eigenvalues will be related to this theta, plus and minus. So that's algebraic way of doing the same thing. I guess this deriving this should be not that difficult, because psi essentially you put instead of alpha sine of half of the angle, and instead of the beta cosine of the half of the angle, and then you could derive this easily. Okay, so this is something about the simple cases, and now the real case. The real case is a little bit more complicated, but it has the same idea. So we will have a Walker operator. It's a two reflections. They called for historical, and well, it actually will make sense. They called select and prepare reflections, and they are organized in the way that will be written here. Yeah. So this is the organization. As you could see, they are more complicated than the ones I just talked in the Grover or amplitude amplification algorithm. And but the idea is the same. We have two reflections, make a product, we get the unitary, and the unitary carries the information we want. Then there's only one step left, is just to extract that information using quantum phase estimation. All right, so what are these select and prepare? What's the idea behind? Let's imagine you have a Hamiltonian, and you you have a Hamiltonian, you decompose it to unitary. So then lambda will be the one norm. That's for normalization purpose, to create the normalized version of the Hamiltonian. And then there will be this special vector that contains essentially all our, it contains the coefficients of the Hamiltonian decomposition in unitaries. But coefficients and unitaries will be separated. Okay, so that's I guess somewhat a complication, and it's needed because these what SKs are fine, but they are 2 to the, let's say, number of qubits, potentially vectors of zeros and ones on this ancilla qubits, right? And they are to create the projectors, right? So the number, actually, you don't need to have 2 to the n states. It depends on how many unitaries do we need, really, in the. Is there a problem? Yeah.
It's almost a two angle, the whole black hole doesn't fit. So
Okay.
we'll
Okay. So how far can I go? Is it,
I moved it every time, it didn't, it's fine.
okay. All right, cool. So essentially the number of these states related to number of unitaries we need, and related in a nice way, logarithmically. So we can, for 2 unitaries, use just a 0 and 1 state projectors, right? For 2 unitaries. Then if you have 4 unitaries, then it will be 4 states that are coming from the 2 ancilla qubits, right? So the purpose of this states effectively is to zeros and ones, is to create the projectors that separates the unitaries so that overall construction is still a reflection. And one kind of additional comment here is that the unitaries that we will be using in the Hamiltonian decomposition, they are also actually reflections, so that when we multiply them with projectors, we're gonna get something that we square it, then we get identity, both in the target space and ancilla space, and so the total identity. Easy to see. Just remind that pk prime would be always delta k prime, and then uk with the uk squared will be identities, and so then you could easily show that. Okay, so that's the select part of the Walker, and then there is a prepare part which doesn't do anything on the target state, but it does this sort of reflection around this special vector, and that special vector contains all the coefficients for the Hamiltonian encoding in terms of unitaries. Okay. Now we could see through algebra that actually this Walker operator, well, what we want to see is this magic gives us what we want. What we want is as operator that is in 2-dimensional subspace of our states that I'll just specify in a moment. Will look like this, like the stuff on top, right? So then, if that's the case, this is unitary clear by construction, since this is a reflection, these are the reflections too. And so overall, it's 2 reflections, they don't commute. That is easy to check. And then the only thing is that, okay, what are the eigenvalues can we get from this? Because from this, it's not obvious that it should look like what is on top, right? Because what happens here is that we spread out the information in a very weird way, and after the claim is after combining all that, it will look like this nicely and will give us phases. Okay, why is that? How do we really convince ourselves that that's indeed the situation? So the states where this Walker operator will be 2x2 matrix, those states are the following. So one state will be, I'll call it psi. That state, of course, will be product of state that is, let's say, eigenvalue, or sorry, eigenstate, and let's just say it's a jth eigenstate of our Hamiltonian, right? So our Hamiltonian has a sorry, it's a state Ej, and it produces Ej eigenvalue. Okay, and now we will be using normalized Hamiltonian. So that means the Ej state will produce Ej tilde eigenvalue, and Ej tilde is just simply Ej divided by lambda. Okay. All right. So this is eigen state of the Hamiltonian, and then there will be this V state for the ancilla qubits. So this is the first state, and then we will also construct the orthogonal state to it. And this subspace of this state and this orthogonal complement, this Walker operator we will see will look like really nice. Will look like Ej tilde, then square root of 1 minus Ej tilde squared minus square root of 1 minus Ej tilde squared and Ej tilde. Right, so in that subspace, it will look like we want it, and then we could write it simply as a exponential function of our cosine of Ej tilde sigma y, and extract its phase, right? And extract that Ej tilde. Okay, so now there are, I guess, two steps left. What is the orthogonal complement? Because if you have a state and we are working like with n qubits on a target, and then log of number of unitaries that we need on the ancilla, let's say m ancilla qubit, so then the space will be 2 to the m plus n, right? So if we fixed one direction, then this is really has a lot of freedom. And so, yeah, let's first we need to define how do we write the complement, and then will be the task of calculating psi Walker psi. That's this element, and then psi Walker psi orthogonal, this element, and then other elements kind of will be obviously could be obtained from this by some manipulations. Okay, so let's do a quick break and reconvene and finish this. Okay, any questions? Yeah.
So we haven't really, or maybe I have not really understood yet how the decomposition into unitaries of the Hamiltonian will actually be done.
That's something that I'll talk after.
Okay. So that's not just like I don't know, John Wigner or something simple.
Well, it could be as simple as Hamiltonian is always linear combination of powers, right?
Yes.
And powers are reflection. So this is your.
Okay,
that could be one case, but there are others, and of course this is the most trivial. The one norm of coefficients here could be improved. So we will talk about improvements. Okay. All right. Let's do a quick break, and after
We want to have a whole blackboard. It might just get very small on the screen at some point.
Okay.
Yeah.
But I can actually fit moving it if you want to. Or do you need the whole blackboard to make
the points. It's not I can just when you put it on the right, they keep it there. If you go to the left, they remove it. This is also fine.
Well, it's also okay. I could actually use less of it, so that just trying to understand how far can I go. So it's up to this point. This it's better to stay on this side, right?
Yeah, but you already wrote it.
Right. Okay, so we're all back. Great. So okay, so the one way to define the orthogonal subspace here is through this formula. Okay, and this formula, what it does, it's simply takes the projector outside. You could say Q psi projector are complementary to projection on the side, and applies it to the result of R with the selected select circuit R. And this form, you could convince yourself if you do this, just look at the orthogonal, like what the psi times psi orthogonal will be. You could see that from this expression, it's just two inner like it's actually two expectation values of are selected subtracted from each other, so you get 0, right? And so this form is useful because it allows us to kind of have a subspace for the two-dimensional subspace for the Walker operator. Okay. Now, once we define the orthogonal complement, so we could write this first matrix element. It's psi, then our prep, and our select psi. Now, because psi itself is a B vector and Ej, if we apply the prep, which is just a 2 v minus 1. So what this is supposed to do is to flip the sign of complementary component of V. There is no complementary component of V because it's only like a V vector on the ancilla, right? So therefore, this is the prep part. This will be just the same as doing V Ej, right? So which is psi. Therefore, we have for this expectation value, we have simply psi, R cell, selected R psi. Now we need to show that this is just Ej. How do we do that? I'll just do the algebra. So we have, let's put J first, then V, and then selected circuit is like I wrote there, UK, projectors, K, V, and Ej. All right, and so now this will appear as a Hamiltonian. How do we get that? It's quite simple actually, because these are vectors like this, right? A linear combination of vectors, right? So we have sum for the first V with the, let's say, square root of ck lambda a here, and then sk. So this is the first V. then you have a summation over, let's say, K1 for the UK, and then UK1, SK1, SK1, then we have a second V, which is a sum over K2, SK2, square root of CK2 divided by lambda. And then if you do the algebra, which is just applying the SKs, they are orthogonal to each other. So you, instead of three sums, you're going to get only a single sum. And the k's in that sum, like, okay, so k coming from different sums should be the same because of orthogonality, this with this and this with this, right? So then you're gonna get instead of square roots, you're gonna get 1 over lambda, and then the square roots will give you ck, uk, sum over k. And that is the h tilde, right? And then this is this part, and so h tilde applied to ej state from the left and right, that gives you ej tilde. So that we essentially shown that the first element is the same as we want it to be, and then the only part that is left is this part, which is just okay, more algebra. And considering, I guess, time, let me leave this for like an exercise. Essentially, we define everything, the psi perpendicular and the psi. So we already seen how the Walker applies to the psi and its components. So it's not that hard to actually do as an exercise and show that this is the square root of 1 minus ej squared, right? So then we get the sort of two-dimensional subspace where, well, we could extract the eigenvalues from. That's how it works. And practically, this is the simple example where if you have only 4 unitaries, this is how a circuit would look like to prepare the initial state. Let's say you have a, well, here the psi is just a target part, 2 ancilla qubits to encode, to be able to encode the controlled unitaries, and then the V part to create the V vector. This is a step-by-step analysis of what's happening in this circuit. So you could see that initially you maybe start with not the same psi that we started. It's a simple state where we have like ancilla qubits and zeros. Then we apply the V, so we're creating this V vector, and this is still on target state. After this controlled unitaries, what the black dots mean, the unitaries applied if there is zeros on ancilla, and empty circles for ones. So then you could see that U1 is applied to this ancilla, U2 is applied for 0, 1, and so on. So every ancilla combination has its own unitary, and you apply another V so that you complete the construction of H. So this is, you can see that the state that you have at the end is the normalized H acting on psi within the ancilla, which is 0, 0. All right, so this is one example of how this could work. And the select circuit, select reflection is corresponding to this part between the V's. Okay. All right. So now, I guess before moving on, any questions regarding the Walker operator?
Yes, I have a question, but I'm struggling to formulate it. So just the element psi walk up psi gives us the energy.
That's right.
I feel this question is super stupid, but why do I want to? That's the one I want. I want the energy. So why do I want the other elements
The other
calculate
elements,
of 1 minus EJ squared? Like, I only want the energy.
because when you apply the operator, right? When you apply operator to the state, you're gonna get generally a vector, right?
Mhm.
And the point here is that okay, that vector is not equal to the initial vector.
Mhm.
Okay, so but we are dealing with two-dimensional subspace. Therefore, whatever you get is a linear combination of what you put in plus some extra stuff. And so if you keep applying, if you keep applying W to the result, you will keep rotating within this two-dimensional subspace. Okay, but you cannot simply, because we don't want to measure the Walker operator. Yes, you could potentially, if you could construct this, right? You could have first problem with the proposal of just taking a psi and measuring W. It's like would be difficult to do because W. Okay, you can implement W, but then yeah, to diagonalize it, to measure it, it's complicated, right? Plus, this psi that we have here, it contains the eigenstate, right? So technically, when we work with the real problems, we are not constructing the psi, we're constructing linear combination. All right, and then there will be kind of, as in the normal quantum phase estimation, there will be multiple angles that we can just will collapse when we do the measurement. We will extract one phase, and that phase will be from one of those two-dimensional subspaces. Okay, so therefore, plus you want to extract the phase, you don't want to do the measurement of the expectation value, right? So, and it's a two-dimensional subspace, which is nice because the information isn't closed in the just two-dimensional subspace. All right, now the rest is going to be about essentially how to reduce the one norm, because this is what is the cost, because essentially you normalize by one norm in all these manipulations, and in order to propagate and get the phase, you need to apply a certain number of times, and that number of times will be increased if you need to reduce the Hamiltonian by that factor, right? So that's the idea why we want to reduce the one norm of the LCU decomposition. Okay, so before going there, this is something that we somewhat discussed in the Adamar test because it's the same idea. So one can ask, okay, what's the lowest one norm possibly can be? And the consideration there, if you have some non-trivial part of the LCU expansion, and you have some possible shift that could be there because Hamiltonian is well, just contain the identity in itself, then doing essentially these simple manipulations where we move the shift to the Hamiltonian, right? And this we don't know exactly what the shift is, but if we apply, like if we minimize the norm with respect to the choice of the shift, it's always going to be moving the spectrum symmetrically around the zero. So you're going to get the spectral range divided by 2 on the left side with the shift that minimizes the norm as much as possible. On the other hand, triangle inequality tells us that this is always, no matter what S is going to be smaller than the one norm, right? So therefore, one norm cannot be smaller than the spectral range divided by 2. And so the only way to break that limit is just go and change the Hamiltonian. Okay, so how can we change the Hamiltonian? That's a dangerous enterprise because we want eigenvalues of the Hamiltonian. If you start changing it, yeah, you may end up getting something that you don't want really. But there is some simple procedures that one can do. One is simply we could do extract the symmetries from the Hamiltonian, and one way to do it is just to represent the Hamiltonian as some symmetric operator plus the rest decomposed using unitaries. Why this is kind of useful is because after all we are in getting the phase, and getting the phase could be done by applying simply well, this shift to the Hamiltonian, and if we have the symmetry operator, right? So apply to the let's say the shift, since the symmetry can be moved around, it's commuting with everything, like with Hamiltonian, mostly H minus S, right? Then when we apply to the system function that is also eigenstate of the symmetry, and this becomes just a number, doesn't really change anything. Okay, so by that we could reduce the norm of the Hamiltonian and essentially get the lower one norm because we put some, like we remove some of the information as a symmetry change. Okay, so heuristically we could find this lower, we could lower lower bound by optimizing. We could use symmetries values like number operator SZ and their polynomials with optimizing A, B, C, D to reduce the one norm of the H minus S. What we usually do is look at the H minus S in terms of Pauli products, and this is the simplest LCU where you could minimize the one norm, optimizing the parameters in S. Okay, and that way sort of reduce what you need to encode in terms of LCU. That was the first proposal. Then we realized that we can go beyond symmetries, because what is actually happening with symmetries or more general construction is that the Hamiltonian in the Fock space contains multiple blocks. Let's say if we focus on a particular symmetry, which is a number of electrons, then you could see that in the Fock space we have part of the Hamiltonian responsible for getting the spectrum of n electrons, also n plus 1, n minus 1. And all these blocks technically can affect what spectral range is. And because the spectral range is simply the difference between maximum eigenvalue minus minimum eigenvalue of the Hamiltonian in the entire space. But we are not interested in the entire space. We're interested only in, say, a certain number of electrons, right? So then if some other number of electrons change these values or makes them like this one larger, this one smaller, we will suffer because of that, even though we are not in the business of estimating the eigenvalues of the Hamiltonian with the wrong number of electrons, right? So the idea here is that we can try to introduce the extra operator, we call it killer. In a moment it will be clear why. So we can introduce this killer operator. So the whole purpose of that is to modify the spectrum of the Hamiltonian, but in the areas, in the blocks that not correspond to the right number of electrons, say, right? So what this killer operator will do is if it meets the function with the right number of electrons, it just creates a zero, right? So it kills the function. and then lets the Hamiltonian act on it, and the result will be the same as if there was no killer, right? But for our functions from the outside of the right number of electrons, this killer, of course, will modify the action of the Hamiltonian. And well, the simple way of building this killer would be taking the right number of electron as a number, subtracting it from the number operator for the electrons, and using this prefactor, and then the rest could be optimized to reduce one norm, okay? Because this prefactor is enough when you see the function, when this meets the function with the right number of electrons, this will turn into 0, okay? And then you can also use square. The reason we don't go beyond the square, because the idea here is that H is the 2-electron operator, and therefore we don't want to subtract something beyond the 2-electron, because there will be no components in fermionic kind of representation. There will be no components that the killer sort of can cancel in the H, right? Because the whole purpose is to reduce one norm of the Hamiltonian. And that's what we are optimizing, these 3 parameters. And we do this optimization using, again, very simple linear combination of unitaries, Pauli products, right? So we can optimize this and this so that H minus K has lower one norm in the Pauli representation. And yeah, this is going beyond symmetries, because K is not really a symmetry of the Hamiltonian due to this extra operators. O and alpha, I guess, doesn't really break the symmetric nature, would not break symmetric nature, but one electron part would. Okay, so how well does this work? And it's always good to, since it's a heuristic approach, we do not optimize the spectral range explicitly, because it would be expensive if we try to optimize K by effectively calculating the spectral range and then changing K, seeing how the spectral range changes, right? So that is horrible. It's not practically possible. But what one can do is, well, what we do essentially is just looking at one norm of Pauli decomposition. And for the model systems where we can look at the spectral range easily, we could see how good is this modification compared to absolutely what could be done the best, which is just projecting to the right number of electrons subspace, right? So this H minus K, if it gives the spectral range which is close to the spectral range of projected Hamiltonian, then it means we're doing really a good job. Essentially, the picture of the spectrum would look like this. So there are this maximum and minimum eigenvalues, and they have drawn number of electrons, say. But the blue ones are the right ones. They just they don't stick out. The red ones define the real spectral range. And what H minus K does, it just changes the values of the spectrum outside of the normal number of electrons and tucks them inside this blue range, right? So then that's what we want, because then the spectral range would be changed, and we cannot do better. Otherwise, we would need to change the spectrum of the right number of electrons. Okay, so these are the results for small molecules. The red bars of the spectral range after introducing the killer, the blue bars are corresponding to the projection of the Hamiltonian in the right number of electrons. So then all the wrong states with the wrong number of electrons, they just projected to 0 and not affecting the spectral range. And so you can see that we're still a little bit higher than the blue bars, but it's within the 1.5%, which is surprisingly good, considering that we are not optimizing spectral range. We're optimizing just now kind of one norm of decomposition. So this is always upper bound for the spectral range. So we optimize an upper bound, but yet we're getting the actual quantity of interest to go down very, very much. Now, one question you may ask is why not to work with just projected Hamiltonian, right? So what would be your answer to that? To work with projection, you need to build a projection. How would you build a projection?
Generally, if you just think about the Fermi-Dirac, or just some kind of projection, you would have an exponential again, right?
You would have what?
An exponential function again of the Hamiltonian, or to do it?
A projection to the number of electrons. It doesn't need to know anything about your Hamiltonian.
Ah, okay.
So we discussed Löwden projection, remember, like projection based on the group theory, right? So projections, like the Löwden projection would be looking like a number of electron operator minus, let's say, all the number of electrons that are not the one that you want. Let's say the one you want I, and then the I minus J. And then J goes, let's say I for water is 10 electron system. But if you have basis set that allows you to have 100 electrons because they're 100 spin orbits, so then this projector would be polynomial of the 100-degree or 99-degree for the yeah, so it's essentially going to be a very complicated operator. That's a very simple answer. Why we don't do this? Instead, we're introducing the scalar operator, which is just a 2-electron operator that does the same thing as a 99, in this case, degree polynomial of 99 electron operator that that projector would be in this case. Okay. All right, so now you could also go in interaction picture and remove, let's say, from the Hamiltonian something that is exactly solvable, because in interaction picture we can construct, this is more like for the exponential form, we can construct the as a Dyson series exponential unitary operator, and then the idea would be that this interaction picture, the part that we need to propagate instead of Hamiltonian would be the conjugated perturbation part that is decomposed using unitary linear recomposition. But the problem mostly is that it's okay, it reduces one norm quite substantially because the H0 part is pretty big. We can do that, hard to Fock solvable fragments, but the issue is that it's time dependent. So it's like the qubitization, for example, is not generally possible for, say, time dependent Hamiltonians. There are issues with that. The algebra, it just doesn't work. There are some works recently where people looked at the qubitization, found a way to do the qubitization. If, let's say, you have say maybe a time dependence that is just a single frequency, but if you go beyond the single frequency, it's not possible. All right, so what unitaries can we use beyond, say, Pauli's? That's what I've been talking so far about. So whatever is left after, say, applying the killer, which is our best technique, we're thinking to decompose in terms of Pauli, but can we do better than that? And the answer, of course, is yes. We could do, say, grouping of anti-commuting Paulis. Why anti-commuting Paulis? Because, well, they're easy to group. You just find the anti-commuting Paulis and normalize the coefficients. And grouping always will reduce one norm that we saw in the previous like consideration of Adamar test, right? So they're like number of measurements depended on the one norm, and so what you are trading off here is the one norm of the coefficients before the grouping to two norm after the grouping, and two norm is always smaller than one norm. Right? So that's a grouping that allows you to make bigger unitaries. And then in fermionic case, we could do something with the fragments that we again already know from the measurement and trotter. So we have these fragments which we can diagonalize, bring to the occupation numbers. And what the occupation numbers allow you to do, they are projectors. And as I was talking before, projectors can always be turned into reflections by this simple formula 2n minus 1, right? So that n's are projectors, n square is n, but r's now then reflections. And so then what you do is you turn all the projectors to reflections and you get more complicated unitaries, right? That are conjugated now with this orbital rotations. And the two electron unitaries coming from the two ends, or single electron unitaries that are coming from a single and one electron part. And so that's how you could do the bigger unitaries as well. So turns out that there is an even more general framework that combines everything, and it's called it originates from Majorana's. Majorana's is one interesting way of writing the fermionic Hamiltonian by instead of working with A and A dagger, work with essentially this Majorana operators, gammas. And the gammas, there are two types. One is sometimes they put plus and minus, sometimes it's just even and odd, but essentially the, let's say, plus gamma is A plus A dagger, Hermitian operator, and minus gamma is I with the A dagger minus A. Okay, so these two, of course, you can recombine them into A and A daggers, but the nice thing about Majoranas is that they have this property, they have their reflections by construction, and also they have this nice property of anti-commutativity. So it's with 2 delta PQ, right? And then with this, actually, they form Clifford algebra. And any product of Majoranas will map to under any mapping, Jordan, Wigner, Brauer, Kitaev, it will be mapped to the products of Paulis. This is a nice property because product of A and A daggers, it maps to multiple Paulis, right? But product of Majoranas maps to a single Pauli. So you may say, all right, so what's the big deal? Go to Paulis. That it's not such a big problem. Just go Jordan Wigner. But on top of that, Majoranas have they're like a bridge between normal fermionic representation and Pauli products, because on the other hand, what they have is that the Hamiltonian can be written as essentially square or like quadratic terms and the quartic terms. You see, if I write the Hamiltonian in terms of Paulis, there will be terms up to n qubit operators. When I write things in terms of Majoranas, they're only quadratic and quartic. So they have this nice feature that it's a polynomial of low degree, because there will be indices with some coefficients, but it's a polynomial of low degree in the Majorana terms, instead of being a polynomial of the high degree in terms of qubit operators. Okay, and I can capitalize on that by considering, okay, so easily I could do LCU as just a product of Majoranas. That's not interesting. It's just a Pauli product. But what I can do is I can just write any general LCU as some simple polynomial of Majoranas that have eigenvalues plus minus 1 and conjugated with some unitaries that rotate Majoranas. So another interesting feature of this Majoranas is that they not only form Clifford algebra, but as we know about Clifford algebras, if this is a generator, like if the Majoranas are generators of the Clifford algebra, then if you combine this with the quadratic terms, this will be a Lie algebra. And then you could use Lie algebra to create Lie group that does the rotation. And that rotation has a nice property that it won't change the degree of polynomial. So if you rotate the quartic quartic polynomial, then you always get the quartic back. You won't create larger, more complicated polynomials. And so one can take the simple polynomials of Majoranas with plus minus 1 eigenvalue. One example would be occupation numbers. They are proportional to quadratic Majoranas. And the occupation numbers, of course, with some 2n minus 1, they will create the reflections. And then you could put some unitaries from the Lie group. And this is essentially the form that one can optimize the coefficients, optimize the orbital rotations or Majorana rotations, and see what is the best decomposition where the coefficients will be having the lowest one norm, right? So this is like the general framework of all these decompositions that I was talking about. So these are some of the examples, like a tensor hypercontraction is one other form where what we do is like just finding orbital rotations, u, mu, and u nu, and what they do, they essentially conjugate the occupation numbers. Those are reflections with some extra a mu nu coefficients. That's the form sometimes used. We suggested, after realizing that it's related to Majoranas, a way where we construct a linear combination of Majoranas for them. So it's like essentially decomposing your 4-degree polynomial in terms of essentially linear combination of Majoranas, Cp gamma p, and for these brackets. So. And there are many more possibilities, like, say, creating the quadratic with linear, because all this could be made unitary or reflections by choosing the coefficients. And with the whole purpose of minimizing the one norm, right? Okay, so results, how does this all work? In general, Pauli, if you look at the one norm, Pauli will be the highest. You cannot go below the spectral range with the same Hamiltonian, and the groupings will be somewhere in between. Okay. Now, for the small systems that we like to play with, this is a general overview that, okay, so that on top, the Pauli decomposition for the Hamiltonian, and then that's 100%, let's say. If you do Pauli, but on the h minus k, you actually can go lower than the absolute lowest without modifying the Hamiltonian, right? So which is a big deal, because no matter how smart you are with the groupings, you will never be able to break this sort of bottom unless you change the Hamiltonian. But changing the Hamiltonian of k allows you to, even with the Pauli decomposition, get below the previous limit. Then there's like groupings you can do with h minus k, and then you could do, well, of course, this would be then the next bottom, right? So the delta E over 2 for h minus k. and it comes relatively close to something that cannot be broken by its projected version. That's for the small molecules we reduce by like a factor of 3 roughly. All right, but if we go to the larger molecules, of course, small molecules, who cares about them? Right, so larger molecules like this of the industrial interest, then we could get higher factors like grouping gives you, compared to naive Pauli, 2 to 10 times better 1 norms, but there's still actually things to improve with the grouping, because if you look at the absolute sort of lowest one can get after introducing the killer, it's like 7 times more than we got using the grouping. So there are more possibilities for smarter groups that reduce the 1 norm technically in these large systems. As for small systems, their grouping is very close to the minimum possible. But in the large systems, there is more space to play.
Is there any like intuition like how that would scale? Because I mean, obviously as your system grows, like the importance of whatever subsystem you have or so, like to the entire space, you will get larger.
It also depends on the basis, right? So
right.
Hard to say what's the actual scaling will be. It probably is related to the mostly the basis relation, like if you consider a system with yes, what is the zero in electronic structure theory in terms of energy is the system that fully decomposed, right? If the electron flies away, then the energy becomes sort of zero, and then it's kinetic energy of the electron. So that's the kind of this is the electronic energy, and the zero is the top. But in the calculations that usually done, we have a basis, and you can easily see virtual orbitals with energy is higher than the zero, right? So then you could go higher than zero in the finite basis calculations. And how do, like, you need to accommodate for all that to really consider how the delta E over 2 would scale with the size of the system. It also depends on the basis. I would assume if your basis is, or at least eventually become more and more accurate, it should go back to this picture where the virtual orbitals cannot be higher than zero, but will saturate. But for that, you need a large probably basis. Anyway, so this is an open question. How is this going to scale? So far, what we mainly looking at is okay. Well, there is this large systems that industrially relevant. Some people wanna say find the catalysts, and then they do, let's say, DMRG calculations or any other classical method, and whether we can do better than DMRG on the quantum computers in principle in future. So in this paper we put together with a group of people, there are some reasons for optimism, like there are some systems where DMRG requires a lot of time and on a classical computer, because you need to increase bond dimension quite far, and that takes a lot of resources, computational time. So with the quantum computers, of course, we're doing estimates now, and with all this bells and whistles, so we can reduce the 1 norm. Some systems turns out to be like more efficiently can be done on a quantum computer, right? But there are still some where DMRG will be quite quite good. So you could get chemical accuracy using DMRG, and then there's no point of running a quantum computer that will be more expensive, right? So yeah, this is a kind of a big picture now on a quantum advantage in quantum chemistry. Ideally, what we want is some sort of intersection of three areas, high utility, that's what the business wants. It's like we want to develop, well, all this is needed for, like, if you want to produce some economic impact, we want to develop the compounds that go into the TVs or catalysts for the production of ammonia, right? Also, it's important to not repeat things that are done by classical calculations well. So it would be nice to understand where are the limits of the classical methods. If someone gives you Hamiltonian, can we say, all right, this Hamiltonian will be difficult for DMRG or will have a large bond dimension, or for multi-reference CI, the other methods. And then in the first time, I guess, before maybe it kind of we get large, really quantum computers, ideally we want systems that are quantum easy, meaning that the kind of the Trotter error or LCU1 norm will be small for these systems, and they will be at the same time hard classically, right? So that's where the intersection would be. So that's what we're looking for generally. That was the somewhat related to the systems I was showing on the previous slide with the compounds. But before we, of course, study these large systems, we also did some studies on the small systems, and the whole point of this study was to see, okay, so we maybe are not yet at the point where we can say, all right, if you give me a Hamiltonian, I can tell you how difficult this Hamiltonian will be for classical methods. But in some systems, we know if we break, say, multiple bonds at the same time, then most of the classical methods, let's say here CISD as an example, for H4, you get the energy error compared to full CI growing, right? And you break all the bonds, and then the system becomes again simple. Right? So there is a classical hardness one can model, at least empirically, on the small systems. And in this work, what we wanted to see is like, is there a reason for the hope that quantum hardness, by quantum hardness, like Trotter error, LCU cost, measurements of BQE, those parameters, they will not grow the same way as a classical, because is there a reason for optimism that quantum hardness will be different? And turns out there is a reason actually for optimism. This is a kind of schematic plot of LCU1 norm. As you could see, quantum hardness actually is not growing in this region where a classical system, well, for classical method system becomes hard, right? It actually becomes easy for quantum methods. The reason, again, is related to the spectral range. When you stretch the bonds, all these levels, they actually come closer to each other rather than spread apart from each other, right? And one only parameter that actually makes so far these quantum methods somewhat dependent on the classical hardness is initial state preparation, right? So how difficult to prepare initial state. And that's a number of, let's say, generators in VQE that's what we were thinking about, like initial unitary to prepare a good initial state with a good overlap with the ground state, say, right? So that thing actually is growing the same way as like just general hardness for classical methods. You stretch bonds, it's becoming harder to prepare initial state. But there's still reason for optimism. This is like a table from the paper. Now, what this table shows is we actually don't suffer as much with the preparation of initial state. Why? Because, let's say this is a number of generators, entanglers, 10, 20, 50. This is geometry. Like these are all hard geometries correlated, say, water stretched with the two bonds. And then the numbers outside the parentheses is the errors in the millihartries, I believe. yeah, 10 to minus 3 atomic units. So you could see here, for example, we are outside of the chemical accuracy. Here we're outside, here outside. But number in parentheses is the overlap. So you could see it's 30% already. So here it's 40 almost, 50%. So then everywhere you could see that we don't need to work as hard as to get the, say, chemical accuracy for preparing the initial state that is already good enough to start the quantum phase estimation, right? Because if you have 30% overlap, that means 1 out of 3 times you're going to get the ground state, right? So you run the algorithm 3 times, you get the ground state. And for classical algorithms, you need to, like PQE, if you don't use QPE, we are still far from the actually chemical accuracy with this number of entanglers, but it's a small number, 10, 20, 50. So that's the point here is that for overlap to get the non-negligible overlap, it's much easier to get the chemical accuracy and energy. Okay. To conclude, quantum chemistry is still an attractive area, and there are lots of interest in algebra. That's why I'm doing this. Hopefully that was clear in a series of these lectures. And the great news is that clearly, I guess, complexity of the systems is quite different for different algorithms, right? So the quantum algorithms have a different set of difficulties than classical algorithms, and that's something to explore further. And then, yeah, more info, I guess I put the lectures on the YouTube channel, but there are some highlights of our works more in depth. You could take a look, and some of the stuff we coded in the free package Tequila by, like it was started by a group of Alanis Perguzic, and now some of his postdoc, Jakob Gottman, for example, is leading the efforts in he's a professor somewhere in Germany. Now, these are the people who are actually responsible for all the progress I was talking about. Well, not all, but the stuff that was coming from my group. So I want to acknowledge former members on top, the current members, this picture, funding, and of course, all of you for kind attention. All right. Any questions? All right, so I guess that's right on time. Okay.
Thank you very much.
Online people, do you have questions? If not, then thanks for listening.